continue what we have left last time. All right. All right, so this is the last examples, right? So we try to solve the problem. We reset the beginning for the logical effort, right? So you have a memory design, right? So which is the 4 to 16 decoder, right? So we know the inputs, we know the outputs, right? So we try to design this decoder so that this decoder will have the fast delay time, right? So shortest delay time will have a faster circuit, right? So before these examples, right, we actually derive a very important just a conclusion here, right? So which is the best stage effort, all right? So the best stage effort here, right? So this is the key important solution, right? Rho equal to 4, right? This rho is not to represent the best number of stage, right? So this rho is to represent the best stage effort, which is f, right, small f value, right? So no matter what kind of the just the input and output value is, right? So if you can try to make the best stage effort equal to 4, then the total delay time will be the minimum, right? So this rho is equal to 4 is the conclusion that we have talked in the last class. All right, so we went through those very lengthy type of equations, right? Try to derive the number of stage, right, versus the total delay time, right? So then eventually we figure out if we pick the rho equal to 4, uh, pretty much the delay time will reach to the minimum. All right. Okay. So then we come back to this this design problem, right? So we have 8 inputs, right? So basically A3 to A0, and you have a complementary inputs, right? A3 to A0 and A3 not to A0 not. So total 8 inputs, and you have a 16 outputs, right? So we revealed the design using a 2 to 4 decoder, right? Instead of a 4 to 16, right? We use a simpler case to demonstrate, right? If you have a 2 to 4 design for a decoder, right? For a single stage, right? If it is a single stage, then you have a 4 inputs, right? You have a 4 outputs, right? But here, for each of the NAND gates, you will have a 2 inputs here, right? So for this case, the branching effort, right, for a specific inputs, for example, right? So this one, you might want to consider this as a separate. Let me make it a full screen. Uh, okay, okay, yeah, I can kill that, right? So I think you can consider this as a separate input, right? So basically you can have a directly S1 not, and this one is S0 not, right? So you have a 4 inputs. For each of the input, you will have a branching effort equal to 2 in this case, right? Because you have a branching here, you also have a branching here, right? So for S1, you have a branching here, you have a branch here. So for each of the inputs, if you consider, for example, the S0, right? Yeah, if you consider S0, right, to one of the outputs, right, for example, the S0 to D0, this pass, right, the branching effort is going to be 2, right? So for this case, B is equal to 2. And we leave the questions to our real problem, right? So what is the real branching effort for the 4 to 16 decoder, right? I'm not sure if you guys think about it, right? So these questions, how can I calculate the branching effort for the 4 to 16 decoder, right? In this case, we are clear, right? So we have a branching effort equal to 2. But if you increase that the inputs, right, inputs to A3, A2, A1, A0, right, A3 not, A2 not, A1 not, A0 not, 8 input, right? And you have a total of 16 of them. What is the branching effort right now? So did you guys think about that? Right, so if, for example, the D0 will be equal to S3, S2, S3 not, S2 not, S1 not, S0 not, right? So D1 will be equal to S3 not, S2 not, S1 naught, and S0, right? And keep going. You have a D15, right? It's equal to S3, S2, S1, and S0, right? So the number of input is changed, number of output is changed, right? And if you consider a single, if you consider the equation of this guy and translate that into the circuit, right? So you actually need to use a four input NAND gate, right? A four input AND gate, right? To, for example, here is S0, S1, S2, S3, right? Not, right? So this will be the D0, right? And you will have another one called the D1, right? Have a four inputs. D2, you have another four inputs, right? All the way to D16, right? So replace all those two input NAND gate, AND gate to a four inputs AND gate, right? And you have a 16 of them, right? So in order to calculate the branching effort, right, you know how many inputs at the beginning, right, and how many inputs has been used for this 16 of AND gate. You should be able to calculate the branching effort, right? For example, here, right? So this is four inputs here. So four inputs times total 16 of them, right? You're gonna have a total 16 of inputs in front of these AND gates, right? And then you have a total 8 inputs, right, from this guy. Right? This 8 inputs, A3 to A0, A3 naught to A0 naught, right? So you have a total 8 inputs here, and you're gonna split them into a 64 of them, and it goes to this 16 of M gate, right? So the branching effort will be a 64 divided by 8, right? There will be 8 branching effort. Okay, so that's the question we have leave the last time, right? So if you get a chance to go back and review this schematic and figure out the branching effort, right? I hope you get the same results here, right? That is the 8, right? Otherwise, it's very difficult to understand why the branching effort is 8. Right? Okay, so if you have that one, and we talked about the last time, right? Let's assuming the logical effort is equal to 1, right? Because you can use a different gate, right, to build this function. For example, here I use an AND gate, right? But I can also use a NAND gate plus an inverter, right? I can also change that to a NOR gate, right, plus another AND gate, for example, right? I can change all the configurations, right? The logic functions can be implemented with a different type of gates, right? So I know every time I change that, the different gates, right, the G value will change, right? So for easy estimation, right, because I want to figure out the number of stage first, right, before I can figure out what kind of a gate I want to use, right? So then at the beginning, I can use a simple way, right? I just assuming G equal to 1, right, and get some ballpark value of the total pass effort, right, which is F, which equal to GBH, right? So the B is equal to 8, right? H, we know that, right? So total output divided by the input, right? Total output capacitance is been given, right? So it's a 32 bits, and each bit is taking a 3 kind of a capacitance, right? So that is, you can use 32 times 3. Input is a 10 unit size transistor, right? Give you the size, then you can get the input capacitance. This is output capacitance for the decoder. This is the input capacitance, right? So you can calculate the capital H, right? No matter how many stage in this decoder, I can always calculate the capital H without knowing the internal path, right? Okay, the branching effort is the difficult part, right? We just discussed that, right? So why the branching effort is equal to 8 for this case, right? Because you can back calculate, for example, here, right? How many total inputs you have used, right? For each of the inputs, you want to figure out for each of the inputs how many gates it has been connected, right? That is my first stage branching effort, right? For the next stage, right, you don't have any branching effort, right? Because each of input outputs, you can either adding an inverter or adding another gates, right, and goes to the output, right? It depending on how many number of a stage we want to design, right? So the only branching effort, the branching design is only happen at the first stage, right? So, okay, at the first stage, you have a total 8 inputs here. And if we use a NAND gate or any other gates, you have to have a 4 inputs, right? To design that, right? Because for the decoder, right? That is how the decoder equation looks like, right? So you got to have the 4 inputs, right? To have the different combinations. So yeah, you have a 16 of them, right? 16 times 4 is a total 64 like inputs need to be putting on the second stage, right? So you know that the first stage output is 8 of them, but input is 16 of them. That you know that for each of the input, you have to branch out and 8 of them, right? So yeah, so that is how you calculate the branching effort. Yeah, because this each of the input is symmetric, right? So okay, so that is the typical part. But if you have the B is being calculated and then H calculated, G assuming is equal to 1 to begin with, right? Then we can calculate the total capital F, right? So pass effort, total pass effort. So which is this value, right? And then remember the equation that we have learned is we want to keep the rho equal to 4, right? So in the rho equal to 4 means so f to the power of 1 over n is equal to 4, right? So if I try to write down the equation here, this guy is so f is equal to this guy, right? Rho equal to 4 means is equal to f to the 1 power of n, right? 1 over n, right? F to the power of 1 over n is equal to 4. And we calculate f value here. So in order to get n is this equation, right? N is to the log 4 to the f, right? So you just use the f value putting in there, and you get number of stage, right? So when you calculate the best number of stage, right, this is the best number of a stage for least amount of for smallest amount of d, right? Okay. You get a value here, right? This value very likely it won't be an integer number, right? So it could be a 3.1, could be 2.3, could be a 4 point something, right? So it depending on the f value, right? So in another word, right? In another word, this best number of a stage is being determined by the total pass effort, not the parasitic delay, right? It's being determined by the total pass effort, right? So then if you have a different pass effort, and this number of a stage will change. All right, for this case, the total pass effort is the 76.8, right, delay, which is, yeah, this is a process independent delay. Right, so then if I plug in these values and calculate the best number of stage, I get a 3.1. All right. Okay, so next question is, oh yeah, is I get a 3.1, so I cannot design a 3.1 stage, right? The number of stage has to be a integer number, right? How can I do? So I mean, the closest number is n equal to 3, right? But you can also try, for example, the n equal to 4, right? Or maybe even try n equal to 2, right? Why you want to do that? Why you want to try all different numbers, right? Instead of just finding the closest integer number to this calculation. Because when we do the estimation, right? When we do the estimation, we have assumed that g is equal to 1. That is there are some arrows here, right? So you know that for the AND gate or for the NOR gate or 4 input NOR gates, right? So that g value is not exactly equal to 1, right? So you will have some variations on the f here, right? So and when you back calculate the best number of stage, that will affect your n number, right? So that means once you have some initial ballpark value, right, to evaluate the total pass effort, you get a number. After that, and you want to try at least like a 3 of them, right? So one number smaller and one number bigger, right? So you want to try n minus 1, n and n plus 1, right? To make sure in this range, let's try to evaluate what is the best number of stage. All right. So basically, this calculation help you to just eliminate the possibility of like a infinity number of impossibility, right? Just help you to reduce the number of a stage to maybe a 2 or 3 stage, right? For example, I can just use this two, n equal to 2, n equal to 3, and n equal to 4 to calculate, rather than I try directly from n equal to 1 and 2 and 3 and 4 and 5 and 6 until I see the trend, right? So this calculation will give you some kind of the ballpark range to begin with, right? You at most you can just try 3 design, right? So 3 different type of design, right? So once you find the median value, all right. Okay, so we can try a 3-stage design to begin with, right? N equal to 3, and let's see what happens, right? I will now draw is the circuit is fairly more complicated, right? So let's see, for example, here, right? If this is the circuit to begin with, right? You have an input inverter as your it's a driving, right? Driving capacitance, right? Which is the size is 10, right? So this is being given in the by the customer. The customer told you, right? Each of the input is being driven by this unit size 10 times the unit size inverter, right? So, and then this is your inputs, right? You don't have to calculate from the previously, right? This is going to be your inputs, all right? So the first stage is the inverter drive this NAND gate, right? This is the first stage, and the second stage is the NAND gate drive an inverter, right? So drive another inverter, and then you will have the output for your decoder. Right, so and this output to decoder, there's a capacitor here, which is the third stage, right? So this is going to be a 3-stage design, right? So you have to know where is the stage, where is this 3-stage exactly, all right? So then you will be able to calculate, okay, if I have a design like this, right? I know, okay, this is my input capacitance here. I know what type of gates, right, have been used, right, in each of the stage. And I know my loading capacitance, right, which is a 32 times 3, right? So it's been given, right? It's been given. So then I should be able to this is you give this 19. That's why you have 19.6, right? Units of a waterline capacitance that give you your capacitance, right? 19.6. Okay, but if you translate that into the circuit, it will be something like this: adding a capacitor, right? That is the third stage. All right. So now it translates to the problem that we can solve, right? You know the number of stage, right? You know the input size, you know the output size. You don't know the size for the intermediate, the gates, the size of the gates in the intermediate nodes, right? So then we should be able to calculate the size of Y and Z so that you can achieve the best delay time. So how can we do that? Right? For this case, I don't have to recalculate the rho, right? Because here the rho we decide that, right? We determine that in the last stage, right? So the rho has been calculated. I know the best number of stage is typically in the three stage, right? So but we will try 2 stage and 4 stage later. All right. So but we start with the 3 stage. This is the question that we have discussed before, right? You know the number of a stage, you know what kind of gates has been used. Let's calculate the capital F, and we get the best stage effort. That is the real value, right? So that is not the estimated value because we know the gates is being used, and then we can calculate the pass effort. All right. So for example, here the logical effort is G, right? Basically, it's the G1 times G2 times G3, right? So the G1 value is 1, right? But inverter, you don't have to think about that, right? You know that. Okay. And 4 inputs NAND gate. Okay. 4 inputs NAND gate. What is the G value? Okay. So yeah, people may say, oh yeah, I need to go back to the tables, right, to check that. If I don't give you the table, you still need to you're still able to calculate the logical effort by yourself. How can we do that? Right, 4 input NAND gates. So first consider NAND gates is how many PMOS and how many NMOS, right, for this case. 4 inputs NAND gates. How many PMOS? Can somebody type in the chat? Tell me. Let me switch back to the chats, right? How many PMOS in the PMOS and NMOS is equal to each other, right? So for the NAND gate, if I have a 4 input NAND gate, how many PMOS? Does anybody know that? wake up a little bit, all right? Okay. Does anybody know? Yes, yeah, that's four inputs, right? That means the gate is connected with the four inputs. So this gate is being tied to PMOS and NMOS gate is tied together, right? So you have four inputs means you have a four PMOS, you have a four NMOS, all right? The next question is for the NAND gate, PMOS is in parallel or is in series? Yeah, PMOS, you have a four. Yeah, the correct answer is a four PMOS and a four NMOS, all right? So then the next question is the PMOS is in parallel or is in series? In parallel, all right? That's correct, okay? So if you don't have the tables, right? So let's figure out four input NAND gates, what is the logical effort, right? So we've we have talked about that, right? So you actually have a four, the eraser works today, all right? You have a four PMOS, right? They are in parallel, and you have a four NMOS, which is in series. Okay, and you can have the A, B, C, right? So here, A, B, C, D, A, B, C, D. Okay. Okay, now that is the schematic, right? So what is the next step to calculate the G value? I have the schematic here. I have a transistor level schematic, right? But in order to calculate the G value, I have to know what? I have to know what? Make it smaller so that I can see your message here, and I can still oh, I don't know how to do that. Sorry. Let's do here. All right. Yes, the size of the PMOS and MOS. Great. All right. Yes, the size of the PMOS and MOS. Then you can calculate the input capacitance here, right? And then compare that to the inverter which delivers some amount of a current. Typically, it's the unisize inverter, right? And which delivers some amount of a current. So in order to have the size properly, right, so that effective resistance is equal to R, right, for both NMOS and the PMOS, what is the size of the PMOS here? What is the size of the PMOS here? 2, right? Great. All right. So yeah, I hope you should be able to know why the size is 2 here. All right. Right, because for each of the NMOS, for each of the PMOS, right, you have to assume the worst case scenario, single PMOS turn on to pull up the output, right? That is the worst case scenario. In this case, the effective resistance has to be equal to R, right? So we calculate the equation is 2R divided by K, right, is equal to R. 2R divided by K, that is for PMOS, right? And it's equal to R, so K is equal to 2, right? So that's why I have a 2, 2, 2, 2 here, right? So basically the size is equal to that the inverter, unisize inverter PMOS, all right? Okay, so how about the NMOS size? In order to, yeah, same kind of a process, right? So in order to have this effective resistance equal to R, this 4 NMOS has to be turned on, right? All of them has to be turned on, right? To pass the currents and pull down the output node to the ground, right? So in order to have effective resistance equal to R, so each of the NMOS will have the resistance is a 1 over 4R, right? 1 over 4R, 1 over 4R, and 1 over 4R. Why? Right, because they are in series, right? So yeah, I make the equal to a 1 over 4R so that they can, when they add them together, right, the total effective resistance will be equal to R, right? Okay, and for NMOS, the calculation is R over K, right? Is equal to 1 over 4R, right? So the K is equal to 4, right? So once you can, yeah, so the step is you calculate the individual transistor effective resistance, and then you will get the size of that transistor, right? Which is 4, 4, 4, 4. Okay, so now you know there's a 4-input NAND gate, right? The schematic, transistor level schematic, and you know the PMOS size and you know the NMOS size, right? Should be able to calculate the G value here. So G2, right? Because that is in the second stage inputs, right? G2 is my total capacitance value, right? For the gates, which is 2 plus 4, right? Because A and A, each of the input is connecting with a 1 PMOS and 1 NMOS, right? The size is 2 and 4, so the gate capacitance is 2 plus 4, all right? And divide by what? Divide by the unit size transistor, which is like this. If I draw that here, is 2 and 1, right? So this is unit size transistor, unit size inverter. Effective resistance for P and N is all equal to R, right? So the input capacitance for this case is 2 plus 1, right? So the total G value, sorry, the G2 value, right? So the second stage, this logical effort for the 4 inputs NAND gate will be 2, right? So that's a simple calculation here. Okay. All right, let me go back to the slides here, right? So G1 is 1, G2 is 2, right? And how about the G3? G3 is another inverter, right? So I mean, the label is a little bit strange here, right? So it should be put here. So times 1. Okay, so I have a total G value, right? And what is the pass effort? Pass effort is the GBH, right? So now I have a G value is equal to 2, right? Which is not equal to 1 as we assumed before, right? The assumptions at the beginning we did it, we're assuming all the logical effort equal to 1, and we get 1 the stage effort, right? But now it's different. Okay, so then what is the branching effort here? Branching effort does not change, right? It's still the same thing. We have a total 8 inputs and we split them, right? So you see into a total 16 of it, right? This is a total 16 of this NAND 3 four input NAND gate, right? So I have a total 16 times the 4 inputs, right? Which is coming from 8 inputs, right? So each of the inputs will be branching out for 8 times, right? So this is the calculation to calculate the branching effort, all right? So times 8, and what is the H, capital H value? H value is always the output capacitance divided by the input capacitance, right? That is typically is the easy one, right? 32, sorry. Okay, here. 32 times 3, right? And divide by the H is what? Is 10, right? So input capacitance. You can calculate the G, can calculate the B, you can calculate the H, right? So the stage effort, F is what? Is the F to the power of 1 over N, right? F is the value here, right? Number of a stage here, in this case, is a 3, right? And we should be able to calculate the D value. D value is N times the F to the power of 1 over N plus the parasitic delay, all right? So the N is a 3, right, times the F to the 1 over 3. F, we can calculate this value, right? And plus the P. P is all the parasitic delay, right? P1, P2, P3. P1 is 1, P3 is 1, P2 value. What is the P2 value here? Parasitic delay for this 4 input and AND gates. Okay, no problem. We have the schematic here already, right? So we have the G value. So what is the P value here? P2 value here is the total output capacitance divided by the inverter, unit size inverter output capacitance, right? So what is the output capacitance here? 2 plus 2 plus 2 plus 2. That is all the PMOS connected here, right, to the outputs, plus 1 the NMOS here, right, 4. right? That is the total output capacitance for the 4-input NAND gates, and divide by the output capacitance of the inverter here in this node, right? So in this node, so that is a 2 plus 1 as well, right? That is the diffusion capacitance. It's the same thing with the gate capacitance, all right, here for the inverter. But the for the output capacitance of the 4-input NAND gate is different, all right? Okay, so this is going to be 2 times 4 is 8, right? 8 plus 2, 8 plus 4, yeah, 12 divided by 3 is equal to 4, right? So you can calculate the p-value without look at the table, right? So you can derive this guy. Once you have this guy and you have the size of the PMOS and NMOS, you should be able to get the G value and the P value, right, by yourself, all right? Okay, once you have the G value and the P value, let's go back to the calculation, right? So this is equal to 4. You should be able to calculate the best delay time, all right? Once you have the best delay time, another question is, what is the size of Y and Z, right? Which is, let me erase some of the writing here. Okay, so much cleaner, right? So what is the size of the Y and Z that we have to use? Oh, why can I erase this? Very strange. Okay, so for example, I still have this 96 capacitance here, right? So that is the last stage. Remember, we always starting to back calculate the size, right? So we always using the last stage, right, to back calculate the size, right? Because if we know the F value, right, F3, F is equal to F3, right? Because you know F2 and F1, they are equal to F, right? So this guy, that means each of the stage, they will have the same stage effort, right? F3, F2, F1, they all equal to each other, right? So F3 is the last stage. F3 is equal to G3 times H3, right? So now we know the F3 value, and we know the G3 value, which is 1, right? And H3 is the size. G3 times the H3 is the 196 divided by Z, right? So then we can also calculate the Z value, right? Z value will be G3 times 196 divided by F3, right? F3 is here, the stage effort we can calculate in the previous stage, right? In the previous steps. Okay, okay, so until here, I think we can solve the problem, right? So let me just erase this, my notes here. I hope I can, I don't know why I cannot erase that. Oh, I apologize. Yeah, for some reason, I cannot erase that anymore. Okay, yeah, never mind, right? I think your slides should have the value there, right? So just open your own slides. You should be able to see the value of F is calculation. I didn't finish the calculation, all right? So, but we have go through that, the equation already, right? So you get F equal to GBH, right? G value, we calculate that, right? Which is equal to 2. B is 8, right? H is 196 divided by 10, right? You get a total is 154. And 154 to the power of 1 over 3, you can get a 5, right? 5.36. Right? This is stage effort, and F, right, which is not the number of stage. All right, this is the total. This is the each stage. This is the best stage effort, right? F value. So that means my F1, first stage, second stage, and the third stage will all equal to 5.36. So that my total pass effort, a total delay time will be the minimum, right? So the total delay time will be using the 3 times F, right? Because each of the stage effort is equal to each other. I just need to multiply 3, right? So number of stage, plus 1 plus 4 plus 1. That is the parasitic delay. And we discussed why the parasitic delay is 4, right? For the NAND gate, right? We can calculate that as well. So total delay time is 22, all right? So 0.1. That is the best delay time for 3-stage delay, right? For 3-stage delay design. Okay, and we have the gate size is we can starting with the Z here, right? Z is the 196 times 1 divided by the 5.36, right? So we have the equation here to calculate the size of the last stage, right? For the inverter Z here, right? Remember, use this equation. G3, right? Here, G3 is equal to 1, right? 19.6 and divided by F3. F3 is equal to F here, right? Okay, and then you can do another step, right? If you have the Z size, and you can calculate the Y, right? Y is G2 times the Z divided by F3, right? G2 is right? G2 value is what? Is we calculated already, right? In the previous stage, right? Which is in my notes here. G2 value is 2, right? So if you use the G2 value here, right, 2, and you have 18, right? 2 times 18, which is the Z, which is your output, second stage output, divided by the F3, we'll get the value of Y. All right. Okay, so apologize, this is too complicated. Let me see if the full screen. Yeah, we'll just get rid of it. Okay, so here, right, this the middle one is what we have tried, right, with the inverter, then 4-gate inverter. This is one of the design, right? You can also try a different, like a 4-stage design, then 4-gate inverter, right? So that is another kind of design because you can change your inputs, right? Not use an inverter to drive. You can use a NAND 4 gates to drive, but input capacitance you can still keep at 4, right? So then you rest of them you can use inverter, right? Adding the inverter. So actually you can see that if you use a 4-stage design, the best case for this type of gate is a 21, right? So a little bit smaller than the even the 3-stage, right? And you can also try 2-stage as well, right? 2-stage NAND gate, then 2-gate, not 2-gate. You can get a 30, right? You can even try a 4-stage with a different type of design. You can get a 19, right? So, which is not too far away from the 3-stage design that we designed at the beginning, right? You see here. Remember the sensitivity we have talked before, right? Once you pick the rho value equal to 4, then you get a number of stage here. That the best stage number, best delay time you get from this one versus the best delay time you do the optimization, that variations within 15%, right? So that's yeah, that is actually approved our before, right? Okay. So that is all the stuff we want to discuss in the logical effort, right? It's a little bit more complicated, right? So once we goes to a multi-stage design, right? At the beginning, we use the case which is we know a number of stage, right? We know the input capacitance, we know the output capacitance, we just don't know the size of the stage in the middle, right? So then now we should be able to size them appropriately and then achieve the best delay time, right? That is the first example we have discussed in logical effort, right? And then we talk about, okay, if I don't know the number of stage, I don't know the design, right? I don't know what kind of a gate. You have the flexibility to change the gate, right? And I just know the input capacitance and output capacitance and what type of gates. Well, I don't know. I can use this method, right? The best number of stage design, right? To estimate using the rho equal to 4, right? Which is the best stage effort equal to 4 to estimate the best number of stage, right? In this case, we estimate the best of a number of stages, 3, and we pick one design to begin with, right? And then we calculate the real G value and real the B value and H value, and we can calculate the best delay time, right? Okay, so you see this yeah, this is kind of the summary, right, for the definition of the stage effort and the path effort, right? So if you only have a one stage, everything will be the lowercase, right? You have the logical effort, you have the electrical effort, branching effort as well, right, which is a small b, and you have the total path effort. Yeah, that is the path effort F, right? G times H, right? So effort delay and parasitic delay. The total delay will be the effort delay plus the parasitic delay. All right. And if you have a pass, right, means you have a multi-stage, right? So you have a capital N here as the number of stage. So the logical effort will be the total logical effort, right? So is a pi gi. So which is you just multiply the g together, right? Will become your total logical effort, right? And the electrical effort will become a capital H, right? Because you have a multi-stage right now. But electrical effort is the last stage output versus the input of the first stage, right? So that is the beauty of this multi-stage pass effort estimation, right? I don't have to care about the intermediate size, right? I can calculate the total electrical effort, right? Because what is the input and then what kind of output I want to drive, that will determine the electrical effort. Okay. The branching effort could be tricky, right? Depending on a function that I want to build, right? So I need to figure out how many inputs coming in as available like inputs, and then how much branch, right? So it's going to be a sticking out, right? To do it depending on the functions, right? So this can need to be figured out. Once we figure out the branching effort, we have the G value we can assuming equal to 1 to begin with, we should be able to get an F value, right, to as a starting point. And once you have the F value, you can have the F to the power of, let's go back to this one, right? Very important calculation here. Once you have the F value being estimated, use the log 4, right, F, then you can get the estimate the best number of stage. And then you can get the best delay time, right? So and then each of the stage effort is always F equal to the capital F to the power of 1 over N, right? And finding the size, right? That is the last step. Once you know the best stage effort, you back calculate each of the stage that the transistor size, right? So remember, we can calculate the gate capacitance value, and you need to know the transistor size is going to be, you need to know what is the P and N ratio, right? So you always need to go back to have the transistor level schematic for each of the gate. Then you can figure out the logical effort, parasitic delay, and also the P and N ratio, right? So then you can know the PMOS size and NMOS size. Okay, so that is all the stuff, right? So there's some limitation here, right? So I think when we discuss this methodology, you probably feel that already, right? We do a lot of assumptions. Remember, right? It's a chicken egg problem, right? Before we design a number of a stage, I need to calculate the total F value, right? So that means I need the G value to calculate the F, right? So, but I don't have the I don't have a number of stage. I don't have the pass. I don't know exactly the G value, right? So that is the one of the limitation of the logical effort estimations. I assuming the G value equal to 1, right? To do the estimation, right? So that is a chicken egg problem. And it also uses the simplest delay models, right? It neglect the input arise time and some other stuff and interconnects as well, right? So that is a very rough first order of magnitude type of estimation, right? Okay, and this is only optimized the maximum speed, right? It does not optimize, okay, the number of layout, the best number of transistor we have used, for example, right? That will changing our layout area, right? So that also impact the cost of my chips, right? When we design it. So yeah, if you just try to optimize the best delay, right, you may sacrifice, let's say, for example, the layout area, you may sacrifice the power consumptions, right, the standby currents, right, so those things, right, because if you increase the number of a transistor, it definitely increase the standby currents, right? I mean, you increase the leakage, you increase the power consumption, right? So those are, yeah, the design parameter or design targets for the logical effort is only to optimize the delay time, right? It does not consider some other design parameter, right? Such as the layout area, such as the power consumption, right, etc. All right. Okay, that pretty much the stuff, right? So here's some assumption here, but yeah, we have discussed that already. Okay. Uh, do you have any questions before I switch to the next chapter? Let me go back to the chat window. Make sure I'm able to see the message that you have. Okay, yeah. So the exam will be including until this logical effort, right? The midterm exam will include all the materials until this logical effort estimation, right? So and the past effort, for examples, I will say anything. Especially something like this, right? The three-stage pass, I give you a number of a stage, and you should be able to calculate the best delay time through this particular pass and calculate the the size of the transistor, for example, right? So those need to be this definitely going to be one of the question, right? So similarly to this type of the problem, right? So and how to estimate the best number of stage, right, also need to be considered. All right. So yeah, so the midterm exam will be until this slice, right, the last slice of this here. All right. Do you have any questions about this logical effort, or maybe a question related to the midterm exam?
I had a couple questions about the homework, specifically question 3. It asks for T rise and T fall. Is that asking for like the propagation delay time or actual T rise and T fall? Because I couldn't find equations for those.
So the T rise and T fall we have discussed using the RC delay estimation. That is not belong to the logical effort, right? I'm assuming that is the questions is going to ask. Remember, that is the chapter you need to go back to the RC delay model, right? So we assuming, okay, if it is the rise time T rise, right? So that means T rise means the output is rising, right? The output rising means the use PMOS, right, to turn on the output, right? So you need to analyze the PMOS that pass. What is the resistance on the P network? What is the capacitance associated with that the P network? What is the output capacitance, right? And then you build that Elmo delay model, right? So you have the RC, that the network, and then calculate the delay. All right, it's going to be a little bit different, right? So then, of course, you can also once you calculate the total R and C, right? So the final number will be like something like, okay, 20 RC, something like that, right? You can compare with the unit size inverter, that RC, right? So which is which we talked at the beginning of this class, right? You can still go back to the original slides here. I don't know how to get rid of this. Okay. Right, so tau is a 3 RC, right? So that is your reference. Once you use the RC delay model to calculate the total R and C, you can divide it by this 3 RC. That will give you your process independent, like a delay estimation. I hope that solved your question.
Yep. Thank
All
you.
right, great. All right, so yeah, because it's kind of combined the previous RC estimation, right? I said RC delay model estimation, right, versus this concept. Right? Okay, any other questions? Right. Let me hold it for a while. Okay, back to this. Let me see the chat message. Any other question? Will we get to bring a sheet of notes? No, there's no cheat sheet allowed. So I will provide all the equations which is you need, right? For this table, Yeah, so G table and P table, right? The logical effort and the parasitic delay, as I said, I'm expected that you will derive those equation by yourself, right? I may provide it as a reference to you, right? Some of the equation here, I may provide it as well. You don't have to memorize those equation, right? But yeah, that's you don't have to bring the sheet of the notes. I mean, it's not allowed, right? Let me make it clear, right? So there's no cheat sheet. No cheat sheet is allowed. All right. Okay, so you can still type in the message here, right? If you have more questions, I will come back and answer that. All right, let's keep going, right? So I think on the next chapter is talk about the wires, right? But I will spend a minimum amount of time to discuss that in the wire. I will quickly go through this, right? In the wires calculations, right? Because yeah, that's it's very important, right? Don't get me wrong. The wires, all the parasitics related with interconnects is very important. I will just go through the slides very quickly, and I will let you guys to use it at after class reading material, right? To study this class, the lecture notes by yourself. All right. We won't have the homework on it, right? But this will be a very good reading material for you, right? To understand. Oh, if I have the questions for you here is, how much the contribution of these wires to your delay time, right? If I running a wire, for example, a few hundred micron, right? So which is very typical, right? So and from the input to the outputs, all between the stage, right? And how much like total capacitance, sorry, the total like a delay time is this wires will be contributed to the delay time, right? So that's some questions. You may assuming that oh, this is all metal wires, right? So this is aluminum or maybe a copper interconnects, and the resistance should be very low, right? And I don't know whether there's some capacitance as well, right? So you may think about the wire may not contribute to the delay too much, right? But this chapter will help you to step by step do some analysis in terms of parasitic capacitance, parasitic resistance, right? And then lead to a conclusion to say, oh, if I have this wire like this length and the and with this width, right? And then what is the RC value I can estimate, right? Also this chapter help you to provide a method to estimate the R and C for a wire, right? So, for example, a piece of wire, should I break it? Should I use a single R and C to represent the wire capacitance and resistance, or should I break it into several of them, right? So yeah, the chapter also mentioned that. Yeah, let's go through that, right? I will point to you some very important conclusions, and you can go through that methodology, right, in the lecture notes and see, oh, how this model is being derived and compared, right, between each other, right? So that will be some very good just reading material for you, right? So as I said, the outline for this chapter is you give some introduction as I did, right? So why the wire is very important, right? What we care is about the wire resistance and the capacitance. So the chapter will start to talk about the resistance value, how to extract that, and what is the real value looks like, what is the capacitance value, where it's come from, right? And how to estimate the delay, and talk about the crosstalk and the wire engineering, right? And how to prevent that with a repeater, right? Okay, so let's quickly go through that, right? Here's the wire kind of a model here, right? You may see, what is this? Why the wire is like that, right? So typically the semiconductor like manufacturing, the wire is being fabricated like this type of shape, right? So it has a certain thickness, you have a certain like a width and the length, right? So the thickness of the wire you you cannot change that. All right. So if you pick a specific technology, right, the thickness of the wire is being given by the foundry, right, by the foundry. So it means when foundry developed a specific process, they have determined the thickness of each of the metal, right? Typically, the thickness is will be increased with the stacking of the metal, right? Top level metal typically is a thicker metal, right? So a T will increase with the number of stacking, all right? So because at a higher, we talk about that at the beginning of the class, right? So at a higher stage, you need to deliver a large amount of current and then distribute them to a single transistor, right? The single transistor is being tapped by metal 1, right? But on the top level, the bond pad is connected maybe with the top metal 4, metal 6, or metal 7, something like that, right? So higher number of metal, typically the thickness is a little bit higher, right? Maybe metal 1 to metal 3, they have the same thickness, which is a thin layer, and then metal 4 is thicker, or maybe a different material, right? So they can switch to aluminum to a copper, or maybe a thick aluminum, right? So you can tell from the name, right? So the thickness does vary, right? But you do not, as a designer, as a circuit designer, we do not, or layout engineer, right? We do not have the flexibility to changing the thickness, right? The only way we can change is the length and width, right? Length is how long you can run this wire, right, to connect it. Width is how wide that we can plot them, right? We can raw them. So so you can go back and see how to calculate the this is some background, right? So as I mentioned, this is a cross section of the wires. You will see you can, this is cross section means, okay, this is when I cut the wire, right, in the cross sectionally, right, you will see this is a different, like a width of the wire, right, and length we cannot see, right, because we cut it in the z directions, right, so we cannot see the length. We can only tell the width, right, if you see my mouse here, right, the width for the bottom metal 1 is changing from, this is small width, this is a wider width, right? So, and you can see the top one, right? Metal 1 to metal 2, 3, typically they have the same like thickness. Metal 4 increase the thickness a little bit. Metal 5 increase further. Metal 6 is also thicker, right? So this is typically a thick aluminum process, right? So you will have a lower resistance for a top metal. So each of the metals, they will have a different resistance, right? So you have to know what kind of a metal you are using, right? So in the modern 45 nanometer process, you will see there's more metal stacking, right? So this is the copper bond is going to be even bigger, right? So there's some like a design rule. You may figure out, oh, there's no active circuit can be put down underneath the bond, right? Because the copper create a lot of stress, right? So mechanical stress. When the mechanical stress here, it's going to affect the transistor, like the threshold and some critical parameter, right? So there's some design rule. You will find out, there people were not able to let you to place the active device underneath the bond, right? There's some technology does require that. Okay, and you can go through this resistance calculation. Typically, it's a sheet resistance, right? So using a square, the number of a square to characterize the total resistance, right? So it's basically a sheet resistance. Okay, so go through that a little bit. We'll see. And copper and aluminum is very commonly used, right? Because the price and the deposition, right? Easy of deposition, right? Gold and silver is some specific process we can use that, right? Create a lot of just a lifetime issue, right? For the gold. And tungsten and molybdenum is also being used as well, right, for a specific process. So this is also sheet resistance, right? Typically, the metal 1 for modern technology, so you will see a 0.8, 80 milliohms, 80 milliohms, or 0.08 ohms per square, right? So you have a number of square. So from this number, you can also tell the thickness of the metal, right? If you get a smaller value here typically means you will have a thicker metal rather than the metal 1, right? So, okay. So then you also find out there's some like a diffusion resistance as well, right? So you can use the diffusion means you use a silicon like a well, right? So silicon N well or P well, either silicide or non-silicide to create some resistor, right? You can also use a polysilicon to create a resistor, okay? So then they have a different like a resistance value. they will also have a different like a current capability and how much current you can pass through those resistor, right? So as a designer, you are this is all the available resistance that you are resistor that you are able to use, right? There are NWL resistor, there are poly resistor, of course there's a metal resistor, right? But if you, in your design, if you want to adding like a 1 kilo ohm resistor, right? Typically we use a poly resistor, right? To as a component, right? Unless you try to use maybe a 1 ohm resistor or maybe a 0.5 ohm resistor, then you can use a metal, right? Otherwise, if you want to use a metal resistor to route like a 1 kilo ohm, right? You need a very long like metal line, right? So that take a lot of area, right? Which is not a very practical, right? So okay, so that's the sheet resistance value and contact resistance, right? So that is also very important, right? Contact resistance means from your contacts, from your metals to the semiconductor and through those vias, right? So it can be can have some resistance as well, right? So those are metals. Metal itself, there's some resistance, but in the contact layer, right, they will create some additional contact resistance. Okay. And if the contacts here, right, and here, you can find out there's some current crowding happens, right? If you're doing this kind of connections, then the current crowding will actually increase the resistance as well, right? Okay. This is the resistance value, right? So for the wire, right, you can read those slides and understand. Oh, there's some. How can I estimate the wire resistance, right? If you talk about the metals, right, and typically we try to connect the transistor interconnects, right? If we want to connect the one transistor to another transistor, for example, the drain side, right? So we talk about the layout at the beginning, right? If we want to connect the drain of the PMOS to the drain of the NMOS and then connect it to the output, we typically use a metal, right? We don't use the poly to connect that, right? Because the poly resistance is sheet resistance is too high, right? So and we use the metal, right? So you can also starting with the metal one and then you route it out with the metal two, right? Or even top level metal, right? To get lower resistance, right? Depending on the metal layer, right? But the metal is typically used for the interconnects between the drain and the source. For gate, we are able to use poly, right, to gate, as we discussed before, right? If you use a gate to use a poly to route the gate, right, there will be more resistance than the metal, right? So you're adding additional resistance to the gate, right? So which is also going to impact your delay time, right? Okay, so the resistance is like that, right? Then you can also consider the capacitance here, right? So you may wondering, I'm running a piece of wire, right? Why there's a capacitance there, right? I mean, there's no capacitor, right? So yeah, the truth is here, right? If you're running the wire, see for example here, right? This is the cross-sectional view of the interconnects in the integrated circuits, right? In the integrated circuits, not a PCB anymore, all right? So it's integrated circuits, and they are very close to each other, right? You have a metal one, you have a metal two here, and stacking very closely. Okay, so and then for example, this light area, which is the white area, that's the metal, right? That is the metal area, and the dark area is the we call it interlayer dielectric, right? ILD. Right? Those are the metals. Those are metals, right? And those are the ILD, right? Interlayer dielectric. And you can tell from the name, it's a dielectric, right? Dielectric means is very similar to the capacitor structure, right? For example, there is a capacitance value between the metal one, right? You see this metal line and this metal line. If you are able to see my mouse here, right? This metal one and the metal, let me make full screen. Yeah, I hope I can. Well, I cannot remove it with full screen. Okay. Sorry. I try to quit the full screen here. Yeah. Okay, let me remove that. Good, I can remove it. you see the this line and this line, right? So yeah, I still need to have a full screen here. Okay, there's two, right? So this is the metal, this is the metal, and this is the interlayer dielectric, right? So between these metals, there will be some like a capacitor associated with a different metal line, right? The metal itself, right, will also have some like a skin effect. Will have some like a capacitance associated with that, but mainly just the metal to metal itself, and the metal one to the metal two. There's some capacitance, right, between the metal one and the metal two. And of course, you have a higher level, right? If you sit in the middle, right, there's like a top, C top, and C bottom, and C intermediate, right? So between the metal two, right? So that is the case. We have to be careful, right? If you go back to the capacitance estimation, this is the, let's say, for example, the metal two, right? You have the metal two to the metal one capacitance, metal two to their neighbor. That if you're running the metal two in parallel, right? For example, the minimum design rule is like a 4 lambda, right? Remember that the value, right? The minimum width is 4 lambda, right? So this is pretty close to each other, right? It's only a 4 lambda distance, few microns, even 0 point some microns, right? So that capacitance is kind of significant, right? It cannot be ignored. So you have the adjacent capacitance, you have a top capacitance, you have a bottom capacitance, right? So that's why you have the total capacitance here, all right? Okay, adding that. Okay, and the slides will tell you how to estimate this capacitance value, right? Which is the using this total area dielectric constants, which is typically is an interlayer dielectric is a silicon dioxide with a different like this addition, right? But mainly the dielectric constants is very similar to the silicon dioxide. It's a 3.9, right? And then you can have some estimation of the area and the distance, right? Which is the the distance between the metal and metals, and the minimum design rule, right? Define that the metal distance, right? So that will give you the distance. Okay, so here give you some value, right? So typically the wire have this 0.2 femtofarad per micron, right? That total wire capacitance for if you lump them together. If you lump them together, right? So lump everything. Yeah, just you have this. Remember, you have this total this capacitance value, right? C top, C bottom plus 2 C adjacent, right? This total capacitance in the range like a 0.2 femtofarad per micron, all right? Compared to the gate capacitance, which is in the range like a 2. Sorry, let me hold it here. The gate capacitance value is typically in the range like a 2 femtofarad per micron. All right, so I mean this value is true for the technology like in the range 4010 nanometer process, 32 nanometer process, right? You can, if you find the process design manuals, right, you will find, oh, for that particular gate, right, they will give you the gate capacitance value, right? And this is of course is related with the gate oxide thickness, right, and also the dielectric constants, right, for the capacitance value, right? So this is the gate capacitance in the range like 2 femtofarad per micron, but wire is also have a capacitance value in the range like a 0.2 femtofarad per micron. That means you are running a wire, right? So for like a 10 micron, right? So you will be able to get a 2 femtofarad capacitance, which is the 1 micron gate length, right? So capacitance, right? And it is very common to run in the wire in the range like a few hundred micron, right? So tens of microns. That is very common, all right? So that's this table actually, I mean, this figure actually give you some kind of the feeling, right? To see, oh, you cannot just underestimate the capacitance value of those wires, which can happens, right, in the real design, all right? So then give you this type of ballpark value, help you to understand the parasitic capacitance value, right, for wire. Okay, so yeah, this is the diffusion capacitance value, right, which is similar to the gate capacitance value, is also 2 femtofarad per microns, right? So and polysilicon, right? That's why we discussed, right? So you also use a diffusion as a resistor to connection, right? But this capacitance value is too high. That's another reason that we don't use the N-well resistor or P-well resistor, right, to as a connection, right? There's some other concern about the well resistor that we call the well resistor. well resistor, right? So we have a poly resistor, right? And we have a metal resistor, right? Right. This is three type of resistor, typically available to be used in the design, right? But diffusion capacitance is too high, which we don't use that. That's the reason we typically don't use the diffusion well resistor or diffusion resistor in the design, right? Because that creates a lot of parasitic capacitance, right? Can slow down your design and slow down your circuit. And polyresistor has a lower C but a higher resistance, right? Which is also not good, right? Because the delay is being contributed by both resistance value and capacitance value, right? So just occasionally running for, I mean, in the real design, very rare case that we can running a very long like a poly line to connect the gates, right? We typically use a metal one to touch the poly, right? And using the metal one as the gate running, gate runner. Okay, so to give you some high level understanding, right? This one is also very important, right? The question is, okay, I can estimate my total resistance value and the total capacitance value if I running a piece of wire, right? So for example, 100 micron with the width of 1 micron, right? For a metal tool, right? If I have a piece of metal running like that, how can I build a good RNC model, right? Remember, for the transistor, right, we do have a good RNC model to break the transistor into an individual capacitor, gate capacitance, diffusion capacitance, right, and channel resistance, right? That's a very good model, right? So RC model, transistor RC model. How can we build a good RC model for a wire, right? So that's the question, right? Here you see there's a three different model here. So the bottom line is we do not use a single resistor, single capacitor, all right? So, but even though we use a single resistor capacitor, there's a three different model that we can use, right? We can use a one resistor, one capacitor, L model. We can use a one resistor, break the capacitance and put into left-hand side and right-hand side, become a pi models. And we can also break the resistor and lump the capacitor together, become a T model, right? So, and then we can, this is a model type, and we can also use a number of segments, right? Means I break the wire into like maybe 100 times, or maybe we will break them into 3 times, right? So I can have a different destination, right? So anyway, so there will be some kind of the discussion, right? So if you go back to the textbook, you can also find out the discussion. But the conclusion is 3 segments pi model is accurate enough to the 3% of variation. That means if you use a pi model, the middle one, right, and break the your total wire resistance and capacitance into 3 segments, means okay, I break the resistor into 3 resistor. I break the total capacitance into a 6 capacitor and connect them like this a pi model, right, in series. And if I calculate that delay in that model, right, of course, we learn the Elmo delay model, right? So if you break them into a different segments and then I use the RNC to calculate, I can get a delay estimation, right, with a different model. So which one is more accurate, right? This is the 3-segment pi model is the one that we typically like, right? Okay, so here is the wires as being used in example, metal 2, 5 millimeter long. Right, to see here is a very extreme case. We're running the wire to across the chips, right? So the chips could be like a few millimeter by a few millimeter, right? And if we're running a wire like across the chips, right, for the left hand side to the maybe top left to the top right, right? So to the bottom right, right? If you're running the wire like that, then you can get a millimeter long wire, all right? So, and if we're running the wire as a minimum length, right, typically 0.3 micron, right? So the minimum length, you can estimate this the delay, right? So out of this metal tube, right? If you use a 3-segment pi model, you break the total resistance into a 3 portion, right? And then you break the capacitance into a 6 portion, and you build this 3-segment pi model, right? And this is the how to model the wire. All right. So yeah, go through that, right, to figure out how you can calculate the sheet resistance, right? This value is being given, right? If you use metal 2 in the 180 nanometer process, then the sheet resistance for the metal 2 is 0.05 ohm per centimeter per square, right? So this is a per square like sheet resistance. And then you use the total length here times this value, right? So you you use the total length divide by the width, right? You get a number of square, right? And then number of square times this 0.005, right? 0.05. You get the ohm, right? You get the resistance value, right? Once you have a resistance value, you break them into a 3 portion, and you can build a pi model, 3-segment pi model, right? For the resistor. Same method, you can calculate the capacitance, right? As I mentioned before, capacitance value is 0.2 femtofarad per micron, right? So you can use that value to estimate your delay. All right. Okay, so I think I haven't finished that. The time is over. Yeah, I'm sorry for the overtime. So we will stop here, and you can start to prepare your midterm by finishing homework 1, 2, 3. I review that, and then we will meet next week. Right. All right. Thank you. Thank you.